Recording is rolling. Welcome to Monday, October 3rd. So here's a big picture layout for this week. We're taking today and tomorrow to finish up forces and Newton's law. I know I haven't seen you guys in almost a week now. We've had a few days off for the hurricane. So we got to wrap up a couple things there. So we're going to do a lab today. And then you guys remember those 60 conceptual questions in this packet? Right, so we did the first 20 is Newton's first law. We did those. Then second law for the second 20 questions. Well, we haven't hit yet our Newton's third law questions, which is the last 20. So we're going to do those tomorrow. And then tomorrow I will also get you guys your next quiz, which is going to be due by the end of this week. So it'll be another open notes take home. Right? But most of the questions will be just straight out that packet. Right? Right, and then Wednesday we'll kickstart the next section, which is going to be these topics. All right, so that is what we're looking at there. Right, let's get to this friction lab. So you guys have this page in front of you, right? You guys got this page. All right, so this friction lab is going to be in two parts. I'll show you guys what to do here at the start. Then most of the class, you guys will be doing this lab with your friends, and then the last about 10 minutes, I'll debrief lab with you guys. All right, so the left half of the lab, the first half, I think this part's a bit more straightforward. And all it involves doing is, see what it says, weight and pulling force, and then take the ratio of those two. So for example, this guy right here, this guy has a mass of 500 grams. Do you guys remember how much 500 grams weighs? How many newtons? Okay. It's really close to 5 newtons. So I'll just call it 5 newtons. Is that all right? Okay. So I got a 5 Newton weight. Right. You guys remember these spring scales? It has two scales on it. One side says grams, the other side says newtons. As what do you measure force in? Grams or newtons? Newtons. So you guys can be using the newton side, right? Okay, just ignore the gram side. Newtons. So I have 5 newtons of weight on the thing. Then can I drag this horizontally across the paper? And notice how I'm dragging it. See how I'm dragging at constant velocity? Guys, constant velocity. What's the acceleration equal to? 0, right? Because constant velocity, there's no change in velocity, which means 0 acceleration. Guys, if there's 0 acceleration, what's the net force? Also 0, right? 0 net force results in 0 acceleration. Hey, maybe I need a picture of that. I need to, you know what I need? Let's do a free body diagram. You guys remember free body diagrams? FBD for what you guys just saw and what you guys are about to do. Okay, so let's get a side look at that. Here's the surface, active surface right there. There was a lab weight, right? Center mass, and I was pulling at constant velocity. Okay, let's put all the forces on this lab weight. Okay. Well, I know one force. What's the force that's going to kickstart everything? It's being pulled down with what? Gravity. Yeah, gravitational force. Oh, wait. So I will label that mg, right? Mass times gravity field could be the weight, right? Weight in newtons. And for example I just did, that was 5 newtons, right? That's a 5 newton force, right? Right. Now, I can't just walk away from the paper here because I'm showing it in free fall, like it fell off the edge of a cliff. So what force is holding it up? The normal force. All right. Good call. I guess remember that from a few days back. Normal force, F sub n. Okay. That could be the block at rest, couldn't it? Okay, just like sitting there, and those two are exactly balanced out. Okay. Now, if I pull strictly horizontally, notice I'm not pulling up or down, I'm pulling strictly horizontally. Okay. Then I'm not going to mess with the vertical forces, right? So the normal force will still match the weight. Okay. Okay. I'll call this F sub pull, like a pulling force. You call it applied force. You can call it spring force because there'll be a spring attached to it somewhere, right? Okay. Now, if I just draw that and walk away, then is that the entire story for constant velocity? You guys are saying no, right? And you're right, because that's showing it accelerating, isn't it? Because there's a net force, right? Which you have to be speeding up, right? Which would be true maybe just like an air hockey table. This is like air hockey puck. But constant velocity, I also need what force? Friction. And should the friction be exactly the same magnitude as the pulling force? If it's going constant velocity? Yeah, it should be. Right. So there it is. There's pulling a block at constant velocity across the surface. Right? All the forces balance out, hence 0 net force, hence 0 acceleration, constant velocity. Is that okay? Right? There you go. There's your free body diagram for that one. Okay. Now, now's a good time to get to the question that we're really trying to answer with this. Here's the question. Let me go ahead and spell this out. What you guys are trying to figure out today is this. What is the coefficient of kinetic friction between the two surfaces? Right? There's your question. Okay, now coefficient of friction, well, coefficient of kinetic friction if it's sliding, right? So I might just call it coefficient of friction, but you guys get the idea, right? Isn't that a material property? Like I see this painted lab weight, maybe like this black paint in this paper, right? Do you guys think there's some, some material property that is what you're trying to get at today, right? Is that okay? Okay. And that coefficient, here it is. It's like this mu sub k. That's coefficient of kinetic friction, right? Coefficient of friction is a ratio of two of the forces on this free body diagram. Which two forces get you coefficient of friction? What's one of the forces, do you think? Coefficient of friction. Do you think you care about the friction force? Yeah, let's put that right here. It's a friction force compared to what? This guy right here, the normal force, right? So, do you think that there's enough there's enough materials at your desk where you can figure this out? Like, if you have a spring scale, you could figure out what each of these forces is, right? And you can just divide those two, right? Point over point, right? Knowing that that's equivalent to that, and that's equivalent to that, right? You guys can figure that out, right? That's pretty much the first half of the lab, and that'll answer that question, won't it? Coefficient of kinetic friction, right there. Point. You guys good? Okay. Right. Can we move on to the second half? All right. Now the second half is a little bit more involved conceptually. So I'm going to set this up for you guys, and but I'll leave a little bit unexplained, but I'll tell you guys. I'll fill this in at the end of class today. Okay. So the second half is going to be a different setup, and you actually just need a different measuring tool. What you're going to do is take this lab weight. Oh, pause right here. I forgot to mention a kind of important technical control detail. So I have this wrapped in paper. That's the control for materials, because this coefficient of friction. Well, do you think that different materials have different coefficients of friction between them? Right, like this paint and whatever surface, or this bare metal and whatever surface, right? So if you want to be really scientific about this, then try to control for the materials. And I might do that by wrapping it in paper. You could also do that, or you could just use like all bare metal weights. Right? So kind of up to you how you want to do that. Okay. All right. So all right, back to here. What if you took this object or this object and you put it on a surface? Maybe there might be a textbook on your desk, maybe just the entire desk, right? And you tilt it up, and at some point it's going to break that friction and slide down a constant velocity. So say constant velocity. Well, I know the first half was constant velocity. This half could be constant velocity. That means still means zero net force, which might help you figure out the answer to the question: what's the coefficient of kinetic friction? Right? But it's going to look more like this. Okay, you got maybe like a block on this incline. Okay. And at some angle theta, it's going to slide down at constant velocity. Hey, do you guys think that if you just knew that angle theta, that would be enough information by itself to be able to determine what is the coefficient of friction between these two surfaces? Like, for example, what if I have like this painted lab weight against this paper and it tilts up? It's like at some angle. And then I replace this regular paper with like sandpaper. Do you think I would need a larger angle for it to slide down at constant velocity? I think I would. Or what if I replace it with wax paper, which is super slippery, super slick wax paper? Do you think it'd be a very small angle that it also would slide down at constant velocity? Just maybe like a few degrees, right? I think that there's some particular angle that lines up with some particular coefficient of friction, right? Let's do a free body diagram for this one too. FBD, free body diagram. And you guys remember this. You see that poster hanging over that door right there? Is pretty much what I'm drawing right here. I'm just recreating them. But you guys have seen this before. Remember, I'm introducing a Cartesian system that runs parallel or perpendicular to that surface. Okay. I know that this lab mass has a weight. mg, just like I did before. It's the same weight, right? So that's the same. Okay. But now I'm gonna re-represent that weight in terms of this new rotated Cartesian axis system. Okay, that weight is partially pushing the block into the surface and partially trying to drag it down the incline. Okay, and this angle here is this angle here. It's the same angle. Right, you guys know that? Okay, and if that's true, then how much does the block actually push into the incline? Well, that's just the cosine component of the weight. That's mg cosine theta. And how much is trying to drag the block along? Well, that's the sine component of the weight, called mg times sine theta. You guys remember all this? Okay. Now there is a support force from the surface, still the normal force. So I'll go and draw that. But remember, that's going to be equivalent in magnitude to mg cosine theta. You guys know that? The same magnitude. Okay, guys see that? Okay. And finally, see if I just leave that and just walk away from the paper, would that block be in equilibrium? No, there'd be a net force. This mg sine theta would be accelerating the block zoom down the incline, which actually might be a good representation for, you guys remember one of the very first labs you guys did with the Hot Wheels cars? Right, put the Hot Wheels car on the incline and went zoom, accelerated down. Okay, that could actually pretty well represent that. But if it's sliding down at constant velocity, I still need a friction force to oppose the motion of the block. So sliding down, friction is the other way. And see how friction is the same magnitude as mg sine theta? You guys that? Right. You guys okay so far? Right. Now, I'm gonna leave that right there. I'm gonna come back at the end of class, last minutes. I'm gonna pick up from that point and explain a little bit more. But for you guys, for your lab, here's what you care about for the second half. Just record the actual weight, for example, 5 Newton weight. I did 5 Newton weight. Right. And the angle that it breaks at. You guys have a protractor on your desk. You guys got a protractor right there? Right. So when you tilt it up at some angle, you can grab this angle. You guys think you can do it? And then this third column says take the tangent of that angle. Now here's where I'm going to leave a little bit of mystery because I'm going to see if you guys can figure this out. But let's suppose the angle was like 17 degrees. I'm just going to make something up. It says take tangent of that angle. Tangent 17 degrees. And I'm getting like 0.30 something. Okay. Okay. You guys can do it? Okay. Now once you guys got your data, you guys think you can make some graphs? Remember the graph? I told you what to do on the title. It's always y versus x, right? So for the first half, pulling force versus weight. For the second half, tangent theta versus the weight. So the weight is on the x-axis for each of the graphs. Okay. And there's a couple of questions at the bottom, so you guys can figure this out. Okay. So I'm going to leave these free body diagrams up here, so you guys can reference these. Okay. And then we're going to stop this recording, walk around, help you guys out with this lab, and then the last 10 minutes of class, I'll debrief this lab with you guys.